This video is about the future of robotics, but not only how this technology will impact the lives of companies, engineers and robotic systems, but also how it's going to impact the lives of people around the world. Computer vision. You may commonly know it in your phone, where you can FaceTime people or use Snapchat and it can detect your face and add filters to your face. You may know it when you unlock your phone, or when you point your camera at your dog and the phone is able to know that there is a dog on the screen.
These are all uses of computer vision.
Cameras work similar to eyes, where you have light entering through the cornea and the pupil, which adjusts to allow various levels of light entering. This will then hit the back of your eye, where the retina is, which can sense the light and convert them into electronic signals. These signals can travel down the optic nerve and into the brain. This is how you process vision and light and how you can see the environment. Cameras work in a similar way. Rather than your eye trying to perceive every single colour individually, it perceives colour with RGB values, meaning red, green and blue. Computers operate the same with an RGB value, where your camera can convert this light into red, green and blue, each having a value between 0 and 255. How this relates to computer vision is that a camera can take a picture of an environment which will have blocks of different colours, each with varying in their ranges. As you can see with the different light levels in my room, one side of my face is lighter than the other, which means that if we're just looking at a one raw RGB value, they'd be all over the place. I'd be covered in different ones. Even my blue shirt consists of lots of different RGB values. As such, we use ranges of values. We want to see all the colours between dark blue and light blue. We want to take pictures of the environment and try and see the ish area of where certain objects are. As such, as you can see, even if we blurred my screen right now, you'd still be able to see an ish area of where the t-shirt is. If you squint your eyes, you'll be able to see whereabouts my torso is based on the average blue area. We can do the same with computer vision by seeing the average colours on the screen here and then saying, if this is where the average blue is, we want to just keep track of where the middle is by doing the height times the width divided. You get the middle. As such, we can use this to track objects, to detect objects. This is the basics of computer vision. By knowing how to determine different colours, we can determine the shape of those colours, we can track those colours, and this can be used in a wide range of applications.
To start this project, I implemented this into a robot owl consisting of cameras and a Raspberry Pi. As you can see, it's looking at the 5 main colours, red, green, blue, black and white, one at a time, and as it views it, it's able to determine what colours these are, as I've tuned and set ranges for each of these colours, which can be seen it detecting correctly. Even though this works, there is still a critical failure. This can be shown when using a gradient colour chart, as seen here, which goes from light to dark. As it progresses, it can know when it's white and when it's black, but doesn't know when it's in the middle. It can't tell when it's grey or when it's looking at a colour it doesn't know. To address this issue, I implemented the unknown category. As there are so many categories that define different shades and names of colours, rather than having to incorporate all of these when we only are looking for the 5 main colours, I instead included an unknown category, meaning that if it is not in the defined range, it reads as unknown, which is successful.
Working in these ranges is like working with percentages. Where we have our perfect desired value of blue, it could be 20% darker or 20% lighter depending on the light levels. As such, we provide this range which says, determining on these environmental factors, we can update and still decide what is our colour. This can work the same with computer detection, where we can, for example, take pictures of my face from all different angles. Then the computer can process this and know that this is what my face looks like. With this, it can scan the environment to look for my face. So when my face is off the screen, it can't see it. When it is off screen, it will see something that it thinks is my face. And depending on the angle, it might be 99% sure, it might be 20% sure it's my face. So even if someone else's face is on the screen, it will know, well, they don't have a beard, they don't have certain features that I have, and as such could determine it's not my face. Well, my face might still be seen from an angle it's not been seen before on the computer, but it can still have a percentage of reliability, a percentage of trust, where you say, oh, if it's still 90% accurate, I still want it to unlock my phone. I still want it to be able to detect my face. As such, you can import these ranges, this percentage, this level of trust.
Before we go on to tracking complex objects like faces, we're first going to demonstrate the fundamentals. This is done by tracking one specific colour. As you can see, we're currently tracking the colour red. I've purposely tuned the code to only track colours of groupings over 300 pixels, so the tracking does not get affected by other red small objects or RGB values read in the room. As such, we're able to successfully track red objects. As you can already see, we're now using two eyes. The reason I have done an improvement of my original code to implement two eyes is to make the code more reliable, as if we're using two cameras to track one object, we're more likely to be able to successfully track the object as we're seeing it from different angles that one camera might not be able to pick up on. As you can see, I'm doing a demonstration to ensure that both the eyes are operating independently, and as you can see, we're able to successfully track objects with both eyes of the cameras. To improve the system further, in this new iteration I've added in extra features that allow the robot to move much faster. The first change was increasing the smoothing factor to allow for more precise and faster movements. The second thing I improved on was the neck movement, as in the previous version the neck was not moving very well as it was only based on the left eye's position. Now in the new iteration, it moves based on the average of both the left and the right eye. As you can see, over various movement, it's still able to operate effectively. And even operating under different lighting conditions, as you can see behind the screen, it's still able to operate effectively. The final improvement added was a dead locking feature. This worked by preventing the robot from moving if it was unable to detect the colour we were looking for. This helped improve the robot drastically, as when it was unable to detect the colour, it would move sporadically and glitch out quite often. By adding in this new feature, it was able to improve the robot's overall reliability and resulted in an overall good system that was able to successfully track objects and move how we would expect to. The overall conclusion and results is that we are able to successfully build a working robot that is able to track and detect colours and objects of one singular colour. This has many applications in robotics and is able to be adapted upon further, but the key fundamentals were demonstrated in this experiment.